Hello guys, so let's have now the next exercise, remaining exercise related to the algebraic extension. Okay, so in this lecture we'll solve some exercise which actually tells you what will be the relations and how to find out the degree of extension also of E over F, where generally in most of the cases we are taking F to be set of rational numbers. Okay, so as we have seen in last lectures, here also let's take say Q of root 3I and Q of root 3 comma I. Okay, now let's see if there is any relation between Q of root 3I and Q of root 3 comma I. Both are different. Okay, both are different extension of Q. So your F is Q, its E1 is this, and its E2 is this. Okay, now Q of root 3 comma I. Once you say that root 3 and I are in Q of root 3 comma I, multiplication of two numbers is again in that field. So root 3 comma I is there in this field, E2. So root 3 into I is there in this field. Once you have root 3 into I is in this field becomes a subfield of E2. So E1 is the subfield of E2. So we wanted to find out the degree of extension. So what we have, it's an extension. So what we have, the relation F is equal to Q is equal to E1. What is your E1? Q of root 3I. What is your E2? Q of root 3 comma I. This is what we have. Now what is this degree of extension? So to find out degree of extension, let's see. Now we are getting what is the relation. So now we'll find out this relation, and you can have the simple minimal polynomial, and which is irreducible, is this x square plus 3. So what is the root of x square plus 3? Plus or minus root 3? Degree 2. So the degree of extension is 2. Okay. Now what is the degree of extension here? Okay, that is the main crux. You can say that how to find out the degree of extension. So root 3 into I is there. Okay, this is safe. Now whether root 3 or I is here or not, that is the main calculation. Now what is the degree of extension of E2 over E1? So what do you think the degree of extension should be? Let's see in other way. Yesterday we have found out that if F is subset of E, subset of K, all these are finite extensions, then degree of extension over K over F is degree of extension of K over E into E over F. This is what we have the relation. Okay, so I will take this is to be K, this is to be E, and this is to be your F. What is this degree of extension? Is 2. So E over F is 2. What I want is this, that K over E. So we will have this relation. What is the degree of extension of K over F? So K over F, root 3 and I. So Q of root 3 comma I over Q. Earlier we have seen what the degree of extension is 4, because we have attached root 3 and I. So Q of root 3 is 2 degree extension. Then we attach I, that is the x square plus 1 polynomial, that is 2. So you can have this one. Okay. So what is that P of x? X square plus 3, x square minus 3 into x square plus 1. X square plus 1, that is your Px, whose roots are plus or minus root 3 plus or minus I, and this is an irreducible polynomial over Q. So for this, so what is the degree? Is 2 into 2, 4. So this K over F is 4. So this is the another idea how to find out in between. Okay, so this is 4, this is 2. You get it? This is to be 2. So this is the degree of extension is 2. So what is the degree of extension of q of root 3 comma I over q of root 3i? It's 2. You can use this way because not in all cases you can find out the polynomials. You can find out the polynomials, but it's difficult. We have the property. Let's use it. That will be the simplest idea. Okay. This is the simplest idea you can have. You can have any elements. Use this property and find out the in between property. Okay. In between degree of extension. That is what one can have. Then in the previous lecture we have seen that if you attach root p, then the q of root p has a degree of extension 2, because what is the irreducible polynomial? That x square minus p. That is what we have. Now if you attach one by one, so the base field f is q, then your e1 is q of root 2, e2 is q of root 2 root 3, e3 is q of root 2 root 3 root 5 and so on. You can continue this. This never ends. The prime number, the number of primes are not finite, so this process remains same. Okay, continue. Okay, what is this degree of extension is 2. What is this? 2 root 3 is attached, or you can have the previous idea. Well, the previous idea also works. Okay, find out the degree of extension of e2 over f. Okay, this is also 2. So in general, what we have, if your e, this is your f. Okay, so if your e is f of root p1, root p2 up to say root p suffix k number of primes, then the degree of extension of e over f is exactly, not less than or equal to, is exactly 2 raised to k. So here you can have 3 primes are there, the degree of extension 2 into 2 into 2, 2 cube. In general, directly you can say this. Okay, this is useful. So if you attach square root of prime numbers to the field of rationals, then you get the degree of extension to be attach that number of primes 2 raised to k. Okay, that is what we have. Okay, so this is the calculation. These are the simple tricks one can use for each calculation. Okay, this is the calculation which will be helpful for other calculations also. Okay, to tricky questions which are there in SET and GATE exams. Okay, so that is what. We can have the next one. Now, what will be the utmost degree of extension given the polynomial? Okay, say for example, if you have the polynomial p of x is equal to x square minus 2. Okay, and I am taking f to be q. Then, if you find out the roots of this polynomial, then it is plus or minus root 2, and I am attaching to that q. You can have round bracket also, you can have square bracket also. Okay, root 2. This degree of extension is 2. Does it depend? This degree of extension depends on this, or does it equal to this? What will be the relation? That will be our next question. Okay, that is what our next question. Okay, so what we have, is there any relation between degree of extension e, degree of extension of e over f, where e is obtained by attaching roots of an irreducible polynomial p of x over f. Okay, so what we have the question, find out the degree of extension, or find out the upper bound of degree of extension of e over the field of rationals we are taking, over the field of rationals f, or f generally over f, with respect to the polynomial p of x, where p of x is an irreducible polynomial over f. Okay, with coefficients from f. And this is an interesting thing you can have. So if p of x is a0 plus a1x to nx plus to n, n is not equal to 0 is an irreducible polynomial okay, it's nomial is an irreducible polynomial, okay, of degree n, then e is equal to of degree n over f. In general case, we generally take f to be rational number. Then e is equal to f of alpha 1, alpha 2, alpha n, okay, alpha n, which are the roots of this polynomial, degree n polynomial, sorry, a n x plus to n. So this is nth degree polynomial, it has n roots, okay, may be repetitive, maybe repetition is allowed, okay, may not be. Generally we are taking distinct roots, okay, distinct roots will be useful, okay. The nth roots, n number of roots, degree n polynomial, attach that n number of roots to the field f, then it becomes an extension of f. Then what is the degree of extension, or what is the upper bound of this degree of extension? And the upper bound of degree of extension is n factorial. Is n factorial. Okay, is n factorial. Why this is? You can have this. Okay. Let's see how it works. Okay. So this degree of extension is less than or equal to n factorial. That is the upper bound. Okay. That is degree of extension of e over f is less than or equal to n factorial. The simple one. Your e1 attach first root f of alpha 1 over f. Then e2 f of alpha 1 alpha 2 and continue this process. So e is equal to continue this process, e is equal to f of alpha 1 alpha 2 up to alpha n. Now alpha 1, what are the polynomial? Okay, that polynomial, take that factor outside, x minus alpha 1, then alpha 2 and so on. Okay, this degree of extension is, yes, what are this degree of extension? 2, then what do you have? Say, or 1, 2, 3 and so on. That is the degree of extension you can have. Okay, minimum degree 2, because if you have degree 1 here, then this alpha 1 is absurd here. Okay, or you can have x minus alpha 1, you can have that one also. Okay, so x minus alpha 1, then this one, x minus alpha 1 into x minus alpha 2 and so on up to x minus alpha n. So this is what we have, e1, e2, en. Okay, and below this we have en minus 1. Okay, en minus 1, that is the, or you can have in the reverse way also. Okay, you can have in the reverse way. Okay, so 1 into 2 into 3 into 4 up to n. So what is the maximum value? Is maximum, not in general, okay, maximum, because they may get repeated. Once you have repetition, just x minus alpha 1 square. Okay, in that case it is less than that. Okay, because we want irreducible polynomial. Okay, so what is the upper bound? Is 1 into 2 into 3 into up to n, and that is nothing but the n factorial. So in here onwards, what we have, this statement: if p of x is a polynomial of degree n whose roots are alpha 1 alpha 2 up to alpha n, okay, of degree n, then the degree, then a field obtained by attaching the roots of that px has degree of extension maximum n factorial, maximum n factorial. Okay, this is important because sometimes you can have a polynomial of degree 3 and the degree of extension is, what do you have? 6. We'll have an exercise, okay, based on this. Let's see. Say you can have lots of example. You can have x cube minus 1 and x cube minus 2 and so on. Okay. Say for example, let's take x cube minus 2. I think you can have that one also. Okay. We'll solve the exercise related to this. Okay. So yeah, x raised to 6. You can have x raised to 6, or generally you can have x cube. Yes, is it? Yes. So let's see. So what is your p of x? You can have in the other way also, x raised to 6 minus 1. So here let's take p of x to be x raised to 6 minus 1 over field f is equal to q. We will solve this exercise and then we'll come to that point. Okay. X raised to 6. Find out the degree of extension of E whose roots lies in that E. Now what is px? Is x raised to 6 minus 1. How we are going to go for this? Is x cube raised to 2. So we have x cube plus 1, x cube minus 1. Once you have x cube minus 1, x cube plus 1, yes, then again factorize. You can have factorization. So the factorization what we have is x minus 1 into 1 plus x square, the first factorization, and the another factorization is x plus 1, this one, 1 minus x plus x square. You can check this. Okay, out of which x minus 1, this polynomial, what are the coefficients? 1 and minus 1, the rational numbers. This coefficients 1 and 1, rational numbers. So these two polynomials get absorbed. What are the roots? So 1 plus x square and 1 minus x plus x square. These are irreducible polynomials over Q. Okay. So what we have? Find out the roots. What is the degree? 2. 2 roots are there. What is the degree? 2. Okay. So what will be the degree of extension of E over F is 4. Okay, is 4 with respect to the polynomial p of x. So remember, so this is not the case that 6 is the degree, therefore the degree of extension is 6. No, then the degree of extension is 4. Why? Because out of these 1 and minus 1, the roots 1 and minus 1, you can put up just value. 1 and minus 1 are the roots and they are rational numbers. So it get absorbed in rational numbers and 4 remains only. The roots which are not rationals, you can attach them. You can find out the roots. Just solve that, find out the roots of that. Okay. What is the maximum upper bound? It's 6 factorial. 4 is less than 6 factorial. Okay. So that is what we can have. That is the calculation. Okay. So similarly, you can have x cube minus 1. Okay. X cube minus 1. X minus 1 factor comes out. What remains? 1 plus x square. 2 roots are there. Just attach them. 2 roots. Okay. You can solve that. Okay. Degree quadratic equation. You can solve that. Okay. That is the calculation. Then you can have lots of calculations. Okay. So in the next lecture we will go now for the normal extension. Okay. That is the calculation. Now this is what algebraic extension. So remember what we have learned till now. What is the meaning of alpha is algebraic over the field f? Okay, so what is the meaning of alpha is algebraic over the field f? If alpha satisfies a polynomial p of x over the field f, that is the coefficient of that p of x are from f. Okay, then we have found out, given an alpha, we have found out the polynomial px which is irreducible and it is monicals. Okay, monicals. Then from the polynomial we have found out degree of extension. Okay. So thank you very much for the first part. Okay, so this is what the algebraic extension all about. In the next lecture, we will go for normal and separable extension. That is the simple thing. Once you understood this, once you see all the videos related to this, so this is the 4th or 5th video, I think. Okay, so see all the videos. Okay, you can use in first 2 lectures there is some noise, so please use the headphones so that you can understand. Yes, for that you should have a basic knowledge of ring theory, complete basic knowledge of ring theory and rings of polynomials. So study first the rings of polynomials, basic last chapter of ring theory, what we have in the syllabus, that is integral domain, principal ideal domain and unique factorization domain, and then come to these lectures. Okay, so this is what our chapter, you can say, 1, that is algebraic extension. Thank you very much. Thank you once again.